Alright, we got a very interesting integral here today. We have the integral from 0 to the infinity of 1 over 1 plus x to the 2022 multiplied by 1 plus x squared. Now this 2022 power is a bit intimidating, but we're going to ignore that for now and just focus on our 1 plus x squared. And because we have a 1 plus x squared, we can actually do a trig substitution. In this case, it would be very beneficial to do x equals tangent of theta. And in this case, this would mean dx equals secant squared theta d theta. So I know it's not the perfect to recognize because we don't have any square roots, which is typically the giveaway for a trig sub. But if we actually do this trig sub right here, it's going to work out nicely. So let's actually plug in everything. First off, we have to change our bounds. So we have x equals tan theta. This is essentially saying that arctan of x equals theta. So if we were to do arctan of 0, we are still just going to get 0. And if we did arctan of our upper bound, which is infinity, we will actually get pi over 2. So now plugging in our values to our actual equation or integral here, 1 plus x to the 2022, that's going to turn into 1 plus tangent to the 2022 of theta. And over here, we are 1 plus x squared. Notice this is actually an identity, 1 plus x squared, but x equals tangent, so 1 plus tangent squared. That's actually going to give us secant squared. So I can rewrite this 1 plus x squared after our substitution as secant squared theta. And now all we have to replace now is our dx, and dx equals secant squared theta d theta. So I'll write that right here. And this is really nice because notice we have a secant squared here in the denominator as well as the numerator, so they both just cancel, go bye-bye. That will just leave us with an integral of 0 to pi over 2 of 1 over 1 plus tangent to the 2022 of theta d theta. And the next thing we would want to do, actually, it's not the perfectly easiest to see, but what we're going to want to do is multiply both the numerator and denominator by cosine to the power of 2022 of theta. And in doing so, we'll get cosine to the 2022 of theta over cosine to the 2022 of theta plus sine to the 2022 of theta. And this doesn't look like it does much if you're new to integration, but this is actually a perfect scenario to use King's rule or King's principle, whatever you call it. And because of that, we can actually go straight to our answer of pi over 4. But I know that's not going to be satisfying to all you who don't know King's rule, so I'm actually going to go through it the long way so you know how this all works. Okay, the first thing we're going to want to do with our integral for King's rule is we're going to do a u substitution. In our case, we're going to do a u substitution of pi over 2 minus theta. This will give us a du of negative d theta. And if we want to rewrite this, this will tell us that d theta equals negative du. And before I actually plug in anything, I want to remind you of two formulas. The first being that sine of pi over 2 minus the variable, in our case theta, will equal cosine theta. And the same applies the other way around. Cosine of pi over 2 minus theta equals sine of theta. So we're actually going to use these when I actually plug in all our bounds and stuff, or bounds, functions, whatever. So if we plug in pi over 2, and here to change our bounds, we will get 0. And if we plug in 0, we'll get a positive pi over 2. And now if we actually plug in everything, so plugging in pi over 2 minus x to cosine to the 2022 theta, we'll get cosine of pi over 2 minus u to the 2022 power. However, cosine of pi over 2 minus a variable equals sine of that variable, so I'm just going to rewrite cosine of the 2022 theta as sine to the 2022 of u based on our u substitution. I can do that for the same cosine that's in the denominator. And as for the sine that's in the denominator, we learn in these formulas over here, this will just turn into a cosine with that same power. And notice we do have a negative du over here, but because it's all multiplied together, I can just pull this negative all the way out front of the integral. Now there's two things I'm going to want to do at this point. First, I'm going to rewrite the integral, and I'm going to use this negative to switch our bounds, because our higher bound is on the bottom, and we don't really like that. That doesn't exactly go well. So now we have the integral from 0 to pi over 2, and all of this is in u. However, notice it's a definite integral. And when we're in a definite integral, we could call the variable whatever the heck we want. So I'm going to rewrite this in terms of theta. So this will be sine to the 2022 theta over sine to the 2022 theta plus cosine to the 2022 theta, and all d theta. And now there's one more thing I'm going to do, and then I'll clear the board for you guys. So this was our, well, up here was our absolute original integral, so I'm just going to call this integral I. And then we did a substitution, but we didn't actually change anything. We just did a substitution. We didn't like add or subtract anything. So this second integral here, which was just modified version of the first, this is still equal to I. We just did some modifications, but anything that actually changed the integral. We just worked with it. And actually, all of these integrals are technically I, because we're not just like randomly adding a +2 or something. We're not changing the integral. They're all the same. We're just working with it algebraically or with calculus, whatever. And so because of that, what we can actually do is we can add some of these integrals together because they're both equal to I. And so what I'm going to do actually, I'll just erase the board right here for you guys. What I'm going to do is erase this specific integral that we worked with. But these two right here, this integral I and this integral I, we're going to add these together. And that seems kind of random without knowing how it all works. This actually goes really well. So on the left-hand side of this equation, we have I plus I. So we're going to be left with 2I. 2I equals this integral plus this integral. Notice that both of these integrals are in terms of theta, and both the integrals' bounds are from 0 to pi over 2. Because of that, what we could do is we can add both the integrands together under the same bound. So we have the integral of 0 to pi over 2 of all the stuff in here, which is going to be cosine 2022 theta over cosine 2022 theta plus sine 2022 theta, d theta. And now, what we could do is we don't need the d theta yet, because what we're going to do is remember I said they're all under the same integral. So we're going to add this integrand under here. So this is going to turn into plus sine to the power of 2022 theta over cosine, or I guess it says sine first, so over sine to the 2022 of theta plus cosine to the 2022 of theta, d theta. And now what we can notice with all this is, notice this is cosine to the 2022 plus sine to the 2022. Over here we have sine to the 2022 plus cosine to the 2022. Sure, these terms are rearranged, but both the denominators are the same. We just have the order of the addition rearranged differently. And because of that, what we could do, we can actually combine these two fractions that are in the integrand together. So because of that, 2I is going to equal the integral from 0 to pi over 2 of this term plus this term all over cosine 2022 over sine 2022. Because it's so much to write, at this point, I'm going to write sine as S and cosine as C, just to make it faster to write. So this will be C to the 2022 plus sine to the 2022, so plus S to the 2022, over C to the 2022 plus S to the 2022. And then d theta, whatever. And notice with this, we have the exact same terms in the numerator and denominator. So these actually just cancel. And they don't cancel to 0, they cancel to 1. So essentially, 2I equals the integral from 0 to pi over 2 of just 1 d theta. Okay, having cleared the board and just simplified everything, remember we got to a point where 2I equals the integral from 0 to pi over 2 of 1 d theta. If we integrate 1 d theta, we're just going to get, or not x, we're going to get theta. And that's evaluated from pi over 2 to 0. If we actually evaluate this thing on the right side, we're going to get that 2I equals just pi over 2. But we're just looking to solve this integral. This integral was our original and it's equal to I. And so to solve for I in this equation down here, we just divide both sides by 2. And we will get that I equals pi over 4. And so that is a long way with King's rule to get to our same answer as before. And if you want a shortcut of how to get there, this is the format for it. So your integral has to be in the form of a to b, and in the integrand, you're going to have f of a plus b minus x over f of a plus b minus x minus, or plus actually, f of x dx. And if you have an integral in this format, this is going to equal a plus, or no, it's going to, yeah, a plus b over 2. Wait, no, my bad. That's going to equal b minus a over 2. Yeah. And if you wanted to go through our specific case, we had, remember how I said sine is, I'm just going to write as s, cosine I'm going to write as c. So essentially what we had was integral from 0 to pi over 2 of cosine, or c to the 2022, over c to the 2022 plus s to the 2022. And then d theta. And this fit the thing perfectly, because remember we said cosine was the same as sine to the pi over 2 minus x, and cosine was the same as pi over 2 minus x. So we have the exact same format here. So a plus b in our case, that's 0 plus pi over 2. So that's where this came from. This a plus b turns into a pi over 2 in both of these parts. And where we just have f of x here, that's what this sign was. And then so that's how we got straight to our answer. B minus a over 2. Pi over 2 minus 0 is just pi over 2, and then divided by 2 turns into our answer of pi over 4. So that is how this whole integral works, and that's the base formula for King's rule.